Okay, let's look at some of the nice properties that depth first search has. So as a result of our DFS algorithm, we will visit every vertex and every edge exactly once. Notice that we start off by marking vertices and edges as unexplored, and then we'll visit each vertex exactly once. If a vertex has already been visited, we don't go back and visit it again. We only call DFS once per vertex. We either call DFS from this side, from some starting vertex, or we call DFS from this side. But either way, before we call DFS, we check to make sure that vertex hasn't yet been explored. So we only ever call DFS, this right algorithm, once per vertex. And we mark every edge as either a discovery edge or a back edge. We don't go back and reevaluate edges that have already been marked and change them. We just mark them from unexplored to either discovery or back, and then we don't rechange them, relabel them. So we label an edge for every edge incident on some vertex as either a discovery edge if it leads to a new vertex that hasn't been encountered, or a back edge if it leads back to a vertex that we had already visited. So we label every edge because each edge is associated with a vertex, and we call DFS on every vertex. So as a result, we visit every vertex and every edge exactly once. Now notice that when we call DFS here from some starting vertex, because we end up calling DFS on all of the vertices in a recursive call on all of the vertices that are reachable from the starting vertex, then when we are finished with this DFS call, once it's completed all of the recursive calls that it ultimately ends up making, then as a result, we visited all of the vertices that are reachable from this starting vertex. So we end up marking all of the vertices and edges that belong to the same connected component as this vertex, everything that V can reach. Okay, so that's one thing to note, that we only ever call DFS from this location for each connected component. So as a result of this call, we do call DFS repeatedly from this side, but when we're finished with it, then we've marked every vertex and edge as visited, which belong to the same connected component as V. So if we had to call DFS from this side multiple times, then that means that our graph had multiple connected components. We'll end up making, as a result of this call, a spanning tree for the entire connected component that V belongs to. And we can create that spanning tree if we take only the discovery edges and we don't include the back edges. So notice that we mark an edge as a discovery edge if it leads to a vertex we haven't encountered, so this is that path which leads to that vertex. Whereas back edges indicate these are kind of extra in the sense that they're leading back to a vertex that we were already able to get to some other way. Okay, so this means that our DFS call to a beginning with some starting vertex V will visit all of the vertices and edges in the connected component that V belongs to. And secondly, the discovery edges labeled from DFS form a spanning tree of the connected component that V belongs to. So if we take only those discovery edges, so here are the discovery edges that we used in a DFS call on this graph. If we take only those discovery edges and nothing else, they induce a spanning tree of this connected component that our starting vertex belongs to. So as a result of DFS, we get a spanning tree for each connected component, which gives us a spanning forest of our original graph. So I want to go back now and analyze the running time of DFS, but before I get to that, let me just remark that intuitively, the DFS algorithm is similar to the classical maze traversal strategy. So the idea is we start at some vertex at the beginning of the maze and follow a path to the next intersection. And along the way, we keep track through breadcrumbs or rope which paths we've already traveled. That way, if we reach a dead end, someplace where we've already encountered, then we can follow those breadcrumbs back to the intersection that has a path of an alternate way that we could go, some other path that we haven't encountered yet. So this is kind of one way that we can think of DFS. Okay, so let's see, how efficient is depth first search? What is its running time? So let's go back again to this, to our algorithm. So remember, we're going to use here, n is the number of vertices we have. This is pretty standard notation. And m is the number of edges. Okay, so how efficient is this? To just mark every vertex and edge as unexplored will be big O of n plus n time, because we have to go through, so here, this for loop. We'll execute this n times, and note that we can set or get a label in constant time. So this first for loop is big O of n, because we go through each of the n vertices and mark them as unexplored. Our second for loop is big O of m, because again, we go through each of the m edges that we have and mark them as unexplored. And now let's look at the next loop. So we go through each vertex and check to see if it hasn't been explored. If it hasn't, we call DFS. If it has been explored, then we don't do anything for that vertex. So let's just evaluate the first two lines here. The total running time of those first two lines is big O of n, because for every vertex we check, has it been explored or not. Now we're going to evaluate this last line separately, because we end up making a few recursive calls in this, and it's dependent on our graph, how many connected components there are, how many recursive calls we'll make for a given starting vertex. So instead, let's evaluate what this call would look like, how much this would cost for one vertex, and we'll sort of add up these recursive calls separately. So we know we're going to call DFS once for each vertex. So we're going to look at the non-recursive overhead of how much it costs to call DFS on, let's say, the first vertex we visit, plus however much it costs to call DFS on the second vertex we visit, and then we'll look at how much it costs to call DFS on the third vertex, and so forth. So for every vertex in our graph, we're just going to add up how much it costs to call DFS on that particular vertex. So we're not counting the recursive overhead here, because we're going to just look at, we know we're going to call DFS on each vertex, so we'll add up how much it cost to call DFS on all of the vertices in our graph. So how much is our DFS call for just a single vertex, not counting the recursive calls that it'll have to make? Well, we can set or get a label in constant time. So getting a label once, this is constant time. Setting a label once, this is constant time. So each of these just individually are constant time operations if we're only executing them once. Figuring out which vertex is on the other end of an edge is also constant time. So the only iteration that we have here is we'll repeat this loop once for each edge that we have. So everything inside here we'll do based on however many edges some vertex has, which could be different for each vertex. Some vertices might have more, some might have less edges. The number of edges that a vertex has is the degree of that vertex. So for our first vertex, the total cost of DFS, not counting our recursive overhead, because we're going to consider each vertex separately, our total cost is the degree of that vertex. Because this is how many times we're going to have to go through this for loop, how many incident edges that vertex has. And then when we call DFS on the second vertex, again, the cost will be the degree of that vertex. So the total cost of calling DFS on every vertex is the sum of degrees of all vertices. So from the handshaking lemma, if you remember from the previous lecture slides on graphs, if we add up the degree of every vertex, the total is 2 times however many edges we have. So our total cost of all of the recursive calls that we make to depth first search, because we know we're only going to call it once per vertex, and within each vertex we have that we go through this for loop, degree of that vertex times, then if we add up the degree of each vertex, the total we get is 2m. So the total cost to DFS here, all of the times that we'll end up calling it for all vertices, is big O of m, where m is the number of edges. So this is, we're counting it this separately. This isn't just one call to DFS, this is counting all of those calls to DFS. Maybe we call it multiple times from here or multiple times from here, but across all of them, the total is big O of m. So our total running time here is big O of n plus m, since we're doing each of these consecutively. So we have now, as promised, we have that depth first search takes big O of n plus m time. As a result of our depth first search, we visit each vertex and edge exactly once. And we do so in such a way that we very carefully label edges as discovery edges or back edges. So if we take only the discovery edges that we used, those discovery edges induce a spanning tree. So each discovery edge, so all discovery edges, induce one spanning tree per connected component. So this gives us a spanning forest. All discovery edges give us a spanning forest, one spanning tree for each connected component that we have. Now, if we have only one connected component, then that means that our graph was connected. Every pair of vertices has a path between them. If we have multiple connected components, then our graph is not connected. But we know what all the different connected components are because we have a spanning tree for each connected component. So we're able to solve some of these basic graph problems just by directly using depth first search. And in fact, we can use them in order to solve other graph problems as well, which you're going to see in the next video.